Okay, hi everyone. Good evening. Thanks for joining us for tonight's webinar. I'm Christina and I run the adult programs at the Bloomingdale Public Library. And I'm so pleased that we got permission tonight to record this. We'll be posting it on our YouTube channel. So if you want to share it with a friend, it should be up on our YouTube channel within about a few days of tonight's live event. All right, so again, I'm Christina, and before I introduce our presenter, I just wanted to remind you guys of some upcoming events we have going on at the library, including October being our annual On the Same Page month, where we celebrate one book. We pick one book between us, Roselle, and Itasca libraries that we choose to read, and then we plan a whole bunch of programs around that book. And this year's theme is art history and art theft. If you're interested in that, please join us for some programs, including next Monday. We're going to be watching a film presentation about great cons and brilliant heists in the movies, and that's with our film expert, Stephen Frenzel. So that's next Monday at 6:30. And then at the end of the month, on Monday the 28th, we're going to have an art historian talk about the most famous art pieces that have been stolen in history. And her program is How to Steal a Masterpiece. And again, that's Monday the 28th at 6:30. So join us for some on the same page fun. And if you are a Bloomingdale, Roselle, or Itasca library card holder, by attending an event and filling out a survey, you get a chance to win a gift card. So great incentives. All right. So now let's introduce our speaker this evening, Michelle Nichols. At her day job, she's the director of public observing at the Adler Planetarium, but this is her fun time. She likes to spend it with us, teaching us about stuff that she really enjoys. So everyone, please remember to ask her lots of questions too, and I'm just going to post in the chat where y'all can do that. Okay, welcome, Michelle. Hi.
Hello, and that's the best introduction I think I've ever gotten. That is so great. Thank you very
Oh,
much.
good.
Yes, this is the time I can talk about fun stuff. And not that my job isn't fun, it really is. But uh, what I really love about this particular talk and why we scheduled it for this particular date is we got some stuff coming up in October that's actually pretty exciting. And I'll do my best to remember to at least mention that there isn't just one comet that we might be able to see in October. Just found out this morning that there may be a second one that might be visible in late October, early November. Unfortunately, this comet is so new, there isn't even an official name for it yet. There isn't even an official orbit calculated for it yet. So I just basically told you all I know about this, but suffice it to say, I'm going to be talking about, among other things, a comet that will be visible in October. But stay tuned. Later, there may be another one that might be visible that was literally just discovered through 2 days ago. So this is really timely. We're doing this program now. So why don't we get started? So we are sharing my screen, so we're just going to dive right in. Okay. All right. In order to talk about comets and asteroids, I need to talk about the formation of the solar system. It's sort of like if you ever saw Carl Sagan's Cosmos TV series. He started off one of the programs, it may have been the first one, basically saying to bake an apple pie first, you must invent the universe. In this case, we aren't going to go quite that far back, but we are going to talk about how our solar system got here because it explains why comets and asteroids are here. All right, first off, all stars start off in giant clouds of gas and dust in space. And this is an example of one of those giant clouds of gas and dust. The dark stuff, the darkest stuff that's in here is dust. Think of dust as like smoke particle sized bits. And then the glowing stuff is gas. In this particular case, the glowing stuff is hydrogen gas for the most part. And hydrogen, being the most abundant stuff in the universe, makes sense that you're going to find a lot of hydrogen gas. Well, you're going to find lots of stuff. In these clouds of gas and dust, you have individual stars that form, and they form from the collapse of portions of this cloud. Some of this material starts to clump together even more and more. That stuff gets really hot in the center and it starts creating its own energy. Voila, you have a star. And so we have an artist rendition of that on the left. We have a real image on the right. And so all those little, they look like little tadpoles, all those little tadpole looking clumps, that is an individual star with a cloud of dust and stuff around it. All right. So now you have a star, you have a cloud of stuff. Well, something starts that cloud spinning and the stuff starts clumping together. And that material is clumping and clumping. Stuff gets stuck together. Stuff hits other stuff. This keeps happening. And as material gets stuck together even more, these objects get bigger and bigger. And you eventually come up with even bigger things. And we call those things planets. Now, there is stuff that gets left over because not everything in a solar system gets incorporated into planets, or if objects are going around those planets, we call those moons. So not everything gets incorporated. There will invariably be stuff left over. It's kind of like when you build something from IKEA, you kind of hope there's nothing left over, because if there's something left over, you go, well, what was that for? Well, in the case of our solar system, you have material that is left over. These are small objects. Some of that stuff rained inward and hit the planets. It was sent there from the gravitational influence of the young planets and our sun. Asteroids and comets hitting the early Earth may be a source of some of Earth's water. So this stuff was actually pretty important. Earth didn't start off with all the water we have. It started off with some, but not all of it. And so some of it came from outside our Earth. It came from other objects in our solar system that contained ice and other material, and that rained down on the early Earth and the rest of the planets too. Well, stuff was sent inward toward the planets. Well, some of it got sent outward as well. Some objects were captured as moons by the early planets. So not all of the moons in our solar system started off as forming around the planets. Some of those were captured by the early planets, like Mars's asteroids, for example, were thought to have been captured asteroids. They're actually not. More than likely, something hit Mars in the distant past, material splashed out, formed a ring around Mars, and some of that stuff clumped together. And so that stuff may actually have formed Mars's two moons. So Mars's two moons may have formed not as a captured asteroid, but because of an asteroid that slammed into Mars a long time ago. Some of the moons in our solar systems are definitely captured asteroids. Some of the objects were left in a belt of material just past the outer planets. We're going to talk about that in a second. Some objects were left in a belt of material in between some of the closer planets. We call that the asteroid belt. A few of these objects escaped our solar system entirely. Some were flung outward so fast they never came back, but not quite everything. Stars in our neighborhood kept some stuff from escaping completely, and that material formed not a belt, but a cloud of material around our solar system. So what did we end up with? We ended up with planets, with some moons, some captured asteroids and other stuff. We were left with a belt of material in between Mars and Jupiter. We call that the asteroid belt. We were left with a belt of material out past Neptune. We call that the Kuiper belt. We were left with this cloud, this sphere of material out well past the distant planets, and we call that the Oort cloud. Right? So all of these have been proven, the asteroid belt, the Kuiper belt. We know about planets and moons and comets and asteroids, but the only one that we have not seen directly is the Oort cloud. It is presumed to exist. It is a theorized group of objects left over from the formation of the solar system, this stuff that was flung outward that didn't escape our solar system entirely. And they surround the sun at very icy distances of hundreds of billions of miles from the sun, up to about 1 trillion miles from the sun. But the reason I say it's theorized is we've never seen an object out that far. This stuff, we probably will never see it out that far. It's too small. The stuff is too small. The individual pieces, too small, too cold, too dark. So wouldn't be surprised if we never actually see anything out that far. Um, but we have spotted objects that their incoming orbits strongly suggest that they came from this very distant region, this sphere of these icy, distant things we call comets. By the way, it is a common misconception that the asteroid belt was a planet that broke apart. That's not true. Um, about the asteroid belt, if you stuck all that stuff together, it would only be about 3% the mass of our moon. So it's not a huge amount of stuff. Um, but it never was a planet that blew apart. This was stuff that never came together to form a planet in the first place. And so it was just a lot of those bits that were left over. Some of that stuff runs into other stuff, and so that definitely happens, but it never was one thing that became many things. It was always many, many pieces. We know of hundreds of thousands of asteroids. And so I'm going to talk more about what asteroids are. So asteroids being the first topic. Now, there was a gentleman by the name of Giuseppe Piazzi, and he discovered what he first thought was a comet on New Year's Day, 1801, from the observatory in Palermo, Italy. Now, what became Italy? Italy was not a country at that point, but Piazzi, this is a drawing that is an allegorical representation of his discovery. I'll get to that in a second, but he named this object Ceres. And this was the patron goddess of Sicily, which is where Palermo is located. Now, this is a representation of his discovery. In here, you can see a representation of a telescope. And actually, we have a telescope at the Adler that does not look too different from this one right here. We've got a mountain in the background, but this object here in the middle is Jupiter. And Jupiter, you can see 4 moons here. You can also see this representation of a goddess right here. That is Ceres. And over here on the right, we have Mars. And so this is representing Mars, Ceres, Jupiter. So that would have been our solar system at that time. Sun, Mercury, Venus, Earth, Mars, Ceres, Jupiter, Saturn, Uranus, and that's it, because Neptune hadn't been discovered yet. Between 1801 and 1808, astronomers tracked down a further 3 of these objects within this region of space. So at this point, your solar system would have consisted of Mercury, Venus, Mars, Mercury, Venus, Earth, Mars, sorry, I did it wrong. I knew I was going to do this. Mercury, Venus, Earth, Mars, Ceres, Pallas, Juno, Vesta, Jupiter, Saturn, Uranus. Neptune was discovered in the mid 1840s. So there was a 5th asteroid, what would later be called, or it would be called an asteroid, discovered in 1845, and it was given the name Astrea. An interest in asteroids as a new class of object was beginning to build. So it wasn't just a few things found in between Mars and Jupiter. Now we had 5 things found. And ever since that time, we've discovered new asteroids just about every single year, and they keep finding them a lot. About 600,000 of them have actual number designations, but we think there's at least 1 million that are out there that have been discovered at this point. Now, where does the word come from? Asteroid, OID, the ending of a word oid means like or resembling. Aster is the Greek word for star. So asteroid meant it was an object that resembled a star, but it was very obvious that it was not a star, that these were objects that lived in between the orbits of Mars and Jupiter. So these were star-like objects that we couldn't actually resolve in our telescopes at the time. But we have been, in the last few years, able to see a handful of these asteroid objects close up. So we're going to jump forward in time. This is the asteroid Ceres. It is the only round asteroid. It likely was not the only ever round asteroid. There probably were other ones that were round, but currently this is the only one that is round. Asteroids are rocky, metallic, or icy bodies that don't have an atmosphere. They're not large enough really to hang on to an atmosphere, but this is the asteroid Ceres. Ceres does contain water ice. Now, you're not looking at ice directly here in this crater right here on Ceres. You're looking at leftover salts as the water ice below the surface kind of oozes upward and the ice turns to a gas and goes off into space. And the salts that are in the water get left behind, and the water ice get left behind. Just think about that for a second. There's water ice on an asteroid. So this is stuff that the same water ice that you've got in your freezer right now, same stuff. So some of those salts and materials get left behind. And so these objects start to remind us of our own planet Earth. Now, here's another picture. I just love seeing these sorts of oblique views that kind of make you feel like this is a place. So this is a portion of Ceres here with a deep crater here and an ice mountain. So there isn't ice on the top of it. The ice is pushing upward from below. So there is definitely ice below the surface on the asteroid Ceres. Now, I mentioned that Ceres is currently the only round asteroid, but this one, Vesta, may very well have been round in the distant past. But this one has been smacked into by other asteroids over time, and so it has lost its roundness. A bunch of it has come off, and those little chunks, those bits, have gone off into space. Well, where do those bits go? Well, some of them have come here to Earth. 5% of all located meteorites here on Earth are from this asteroid, Vesta. How do we know that? Well, the same spacecraft that took this picture here, all right, and this picture and this picture. So these were taken by the Dawn spacecraft, which visited Vesta several years ago, and sorry, Ceres and Vesta several years ago. The Dawn spacecraft took detailed measurements of the materials that make up Vesta and Ceres, and we were able basically to say, yeah, a lot of those those meteorites, those bits that have come down to Earth, a lot of them come from this particular asteroid because the materials match. They match very, very well. So that's pretty cool. Actually, at the Adler, we have at least one meteorite that comes from Vesta that we can say, yeah, it's this one right here. And actually, it's in an exhibit. You can touch it, which is pretty awesome. All right, just to give us a sense of size of asteroids, we've got our moon on the right. We have Vesta on the far left, Ceres in the middle, and all those little itty bitty ones are several others that we've seen up close. And so we have asteroids in our solar system that range from several hundred miles wide for Ceres, all the way down to less than a mile wide. And actually, asteroids can be feet wide. So they can be big ones, they can be small ones. All right. So I wanted to just give you a sense of scale for these asteroids. They are the size of Ceres and smaller. So this one right here is called Bennu. And this particular set of images came from a spacecraft, a different spacecraft, which visited Bennu. called OSIRIS-REx. And the job of the OSIRIS-REx spacecraft was to study this asteroid and to grab some of it and bring it back to Earth for scientists to study. And so if you look at this set of pictures, which I hope is coming through okay on your end, I'll have some static images on my next slide. It's a rubble pile. I mean, you look at it and there's rubble everywhere you're looking. And if we look at the images up close, more rubble. And this stuff is it's a rubble pile of an asteroid. If you tried to actually stand on this asteroid, you wouldn't be able to. You would probably sink right in. It looks very solid, but it's really not. When the OSIRIS-REx spacecraft actually went down to grab some of the material, if the spacecraft hadn't fired its rockets after it went down toward the asteroid, grabbed some of it, if it hadn't fired its rockets to back away from the asteroid would have swallowed the entire spacecraft. It would have just sunk right into this rubble. Here's some of the pieces up close. And we found, since these materials have been returned to Earth, Bennu contains the original ingredients that formed our solar system: carbon, nitrogen, organic compounds. All of this is essential to forming the materials that we have here on Earth. So more than likely where Bennu came from was a long gone, small, primitive ocean world, a world that contained water, probably under its surface. But the asteroid that it came from is no more. Bennu is essentially probably the largest piece of this long gone asteroid. So just shows you how we've got very primitive stuff, but the stuff in our asteroid belt keeps colliding and interacting, and things do hit each other out there in space occasionally. Most of it is empty space. But one time we did one of these collisions on purpose. And so that happened a couple years ago. So a couple years ago, we had the DART mission. And the purpose of the DART mission was to have a spacecraft collide with the asteroid in the center of the frame right here. So we've got a larger one, Didymos, and the small one, Dimorphos. All right. One of the mission's main goals was to see if we could deflect Dimorphos's orbit around Didymos just a little bit. All right. So we wanted to see, could we use asteroid impact as a way to possibly save Earth in the future? We wanted to see, could this technique even work at all? Don't worry, this set of asteroids is not headed to Earth. We purposely picked a set of asteroids that had nothing to do with Earth. We didn't want to take any chance that we screwed something up and have this come toward Earth. So that's not going to happen. But we wanted to send a spacecraft at 4 miles a second at Dimorphos, and hit it. All right. Dimorphos is about 400 feet across. Didymos is about 2,000 feet across. So could we smack into the small one and change its orbit around the big one detectably? That was the question. All right. So here is Dimorphos up close. All right. It's about, 400 feet across is maybe about half the size of Soldier Field. All right. So just to give you a sense of scale. So here it is. It's getting close. 4 miles a second. It was going to slam into this part of Dimorphos right here. And the spacecraft, here's an outline of it on the outline of these rocks. All right. Slammed in at 4 miles a second. So what happened? Well, here is actual imagery of the impact, the aftermath. All right. So this is looking at it from Earth. Here is looking at it from a spacecraft that was along for the ride. And so here's one set of images. And this is really amazing because you can see that stuff that had splashed out of the asteroid. Here is another set. This is from the Hubble Space Telescope. It did not take long to learn just how much of an impact this spacecraft had made. Just a little over 2 weeks after we intentionally rammed a spacecraft into this asteroid, the science investigation team realized that we changed the timing of the orbit of the little one around the big one by more than half an hour. We were hoping for at least, about 30 seconds um, of change, maybe a minute, maybe a couple minutes. No, half an hour. So after the nudge to the asteroid, we went from the small asteroid around the big one orbiting in 11 hours and 55 minutes. We shortened its orbit to 11 hours and 23 minutes. Here's another set of images. This is from the Webb Space Telescope. They continued digging into the data, and what they realized was, if you see the stuff that's splashing out of the asteroid, that gave the asteroid a significant recoil. And this impact displaced more than 20 million pounds of rubble from this asteroid and launched it into space. Here is a 6,000-mile long plume created by the impact, which greatly exceeded any expectation for what might have happened. So the orbital change was about half an hour. What would that truly result in? Would that save Earth? Well, in the future, if we know about an asteroid that might be on its way long enough in advance, I'm talking decades in advance. We're not talking if we find it tomorrow and it's gonna hit us in a week. That wouldn't help us. But a small change in velocity now with this um, impact would result in a very large change in space in the distant future. As the diameter of Earth is about 8,000 miles, an asteroid impact like this could be avoided if something like this was headed toward Earth. A hypothetical asteroid impact could be avoided with as little of a shift of 4,000 miles, right? Think 4,000 miles if something's coming straight at us and you need to shift its position in space by 4,000 miles. How do you do that? Change the speed of this thing by 1 inch per second. And that will result in a 4,000-mile shift in about 10 years. So if we were able to find an asteroid that might hit us, do it far enough in advance, build the spacecraft, launch it, impact, and do that at least 10 years in advance, we might be able to save our planet. It's only a start. Don't worry, nothing that we know of is headed toward Earth. We don't know of anything that is going to actually harm Earth in any global way. But at least it proved a point. It proved that this asteroid impact could release huge amounts of stuff into space and cause a big recoil, a big change in velocity of an object like this. And by big, I mean we changed a 400-foot wide asteroid speed by 1 inch per second. So that's actually pretty significant. It's pretty awesome. You got to wonder, who are these cool people who get to have a job where they get to think, what would happen if we run a spacecraft into an asteroid? Well, they got to find out. All right, comets. I love comets. Now, comets were seen as omens of doom by some folks in the past. This is a drawing of a comet from 1665. And there were a couple comets that were visible in 1664 and 1665, and these were bright enough that they would make it into certain books and artworks and other things. And so in this case, you can see this is showing you the change in size of the tail of the comet over time. So every single one of these is a particular day. Now, why is there no tail for the 10th and the 11th of whatever month this was? Oh, April 1665, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th. Why nothing on the 10th and the 11th? It was cloudy. Then visible on the 12th. Why nothing on the 13th? It was cloudy. So you can see the change in size of the tail of the comet. Now, this portent of doom was very common, especially in Europe. This was the Great Comet of 1680. Look at the size of the tail of that thing. But what I find interesting is you can see the folks down here in the crowd, and they're using instruments to study it. They're using measuring tools. But this was something that people would get out and actually take a look at this, just like I do now for taking telescopes out, which is pretty awesome. Now, this is a drawing of a comet. Um, Now, over time, scientists learned that comet orbits are parabolas. Their orbits are not circular, they're more oval shaped. This is a drawing from a book that Isaac Newton wrote, but he's showing you this oval shape of a comet's orbit. And you can see this wispy part here at the bottom, that would be the comet's tail. Um, where Edmund Halley gets the notoriety, why does he get a comet named after him? Well, he determined that the comets of the years 1456, 1531, 1607, and 1682 were the same comet. So he made a prediction that that comet would return in 1758 and return to our part of the solar system. So it wasn't that he was the first person to discover a comet. No, by far, no. He was the first person to figure out, he wasn't even the first person to figure out that comet orbits were ovals. He was the first person to figure out that comets orbited the sun and that you could trace a comet's orbit back and see, could that be the same comet? And so that particular comet was named for him. We call it Halley's Comet. He did not live to witness the comet's return in 1758, but when it did, that's when it started being called Halley's Comet. And since then, if you discover a comet, it is named for you. So while he did not discover this comet, he still made a significant discovery that comets do orbit the sun and return. All right. This is the 1910 appearance of Halley's Comet. And down at the bottom right is a fun drawing. And people thought that the return of Halley's Comet would cause the end of the world. It says fin du monde, end of the world, on May 19th, 1910. Well, that didn't happen. But why were people thinking that? Well, Earth was going to pass through some of the material of Halley's Comet's tail. And it was discovered that the comet's tail contained, among other things, cyanide. And it's just a material that is in a comet, or excuse me, cyanogen, not cyanide, but cyanogen. And people thought, uh-oh, if we're going to pass through the cyanogen in the tail, is that going to rain poison down on Earth? And the answer is no, no, because we have an atmosphere to protect us. But that didn't stop people from selling comet pills and gas masks and all sorts of things, predicting the end of the world. The world did not end on May 19th, 1910 because of Halley's Comet. This was a picture of Halley's Comet in 1986. This is a picture of Comet Hyakutake. It was visible in early 1996. I remember that one vividly. And this one is Comet Hale-Bopp. Sometimes comets are named for two people if they independently discover it and it's within days of each other, then sometimes a comet is named for both people. So Alan Hale, Thomas Bopp, it's a hyphenated name for both. We'll come back to the different kinds of colors and shapes that you see in this picture in just a second. This one was called Comet McNaught. And some people got to see this comet in the daytime. This was in 2007. The reason you are probably thinking, wait a minute, I don't remember seeing a comet in the daytime in 2007, that's because it really was only easily visible in the southern hemisphere. So we did not get to see Comet McNaught like this in the sky. But we'll talk about comet tails in just a second. So what you're seeing is an amazing striated comet tail here. But what is making all this to begin with? So this is not a close-up image of a comet. These are close-up images of comets. Comets are leftovers from the formation of the solar system. They generally formed from materials that were farther from our sun in regions that were colder. Comets share lots of characteristics with asteroids. We used to tend to think of them as completely separate objects, but they're really not. Comets are uh, they're colloquially called snowy dirt balls or dirty snowballs in space, but they're actually mostly rock, sand, that kind of consistency. We'll talk more about that in a second. They're generally anywhere from a few miles across to tens of miles across. They're no more than about 50% ice. So there are ices contained in these comets, but they're not mostly ice. They're actually mostly sandy type material. But they're very sandy, they're very dusty, some ices, but the actual object part of the comet that you can see in all these pictures is called the nucleus, right? So each of these, Comet Borrelly, Comet Wilt 2, Comet Halley, those are the sources of the material which comes off that forms the comet's tail. Again, we'll talk more about that in just a little bit. First off, we have, just like we've run into an asteroid in the past, we've run into a comet in the past on purpose. And it was this one, Comet Tempel 1 in 2005. But this shows us more about what a comet is like. They look very solid. Like if I go back to these pictures here, just like the asteroids, they look like they're solid rock, like you could stand on one of these things. But again, you really can't. Thanks to missions like Deep Impact, we found that the interiors of comets are about as fluffy as cappuccino foam. Think about that next time you get a cappuccino. And they're formed of dust and pebbles and ices that are barely held together by gravity. This material is held together more weakly than think of the snow in a snowbank. That's kind of the consistency that we're talking about. Again, they look really solid, but they're really not. This is a color image, a close-up color image of the nucleus of a comet. It looks very bright. It's actually almost as black as coal. The colors in this image have not been enhanced, just brightened, so you could actually see them in the picture. And let's look up close. Check out all the rubble, all the little pieces. And as you get closer and closer, you see more and more of this stuff. Comets are made of sand and clay and carbon dioxide ice and water ice and methane ice, ammonia ice, methanol, hydrogen cyanide, formaldehyde, ethanol, ethane, amino acids, hydrocarbons, all sorts of stuff. And this is the comets are really neat to study because, again, just like studying asteroids tells us about the early solar system, comets tell us about the early solar system as well. And more about comets. So I mentioned the tail. Where in the world does that come from? How do we go from this chunk of stuff to this really long, amazing looking tail? As comets get close to the sun, the light and the heat causes those bits of ices to turn directly from a solid to a gas. We call that sublimation. And in that process, dust and pebbles are released into space. And so that stuff goes outward and that forms a comet's tail. And you can see the material here escaping from this particular comet. which is called Comet 67P, Churyumov-Gerasimenko. And so you can actually see this stuff escaping from Comet 67P. Well, that stuff goes out. So comets often form multiple tails and trails, and those features are made of different components. First off, from the pebbles. So this is called the dust trail. The dust trail is made of particles that are about the size of sand grains and pebbles, so stuff a little bit bigger. This stuff is released from the nucleus, and this material continues to orbit the sun along with the comet. And this material eventually spreads out into the comet's orbit, and that whole train of stuff orbits the sun as well. If the Earth runs into the trail of one of these debris trails, you get a meteor shower, like the Perseid meteor shower, the Geminid meteor shower. Those meteor showers, you see those quick streaks of light in the sky when the meteors are burning up above you. You're seeing comet material burning up. This stuff used to be incorporated into one or more comets. And so that's the dust trail, the bigger stuff that orbits along with the comet in space in its orbit. Now, this other label here, gas tail. Gas tails are made of gas. So the gas tails are blown directly away from the sun. And so this gas escapes, and the sun's energy pushes that gas tail directly away from the sun. The gas tails are generally made of carbon monoxide gas, carbon dioxide gas, nitrogen gas, and they glow different colors depending on the gas that's glowing. So you might get a blue tail, you might get a green tail, just depends on the different kinds of gases that are glowing. Then finally, the dust tail. So the dust tail is made of dust the size of cigarette smoke particles. And this stuff gets blown outward from the comet, but because this stuff is a little bigger, that material doesn't move away from the comet quite as fast. And so the dust tail tends to be curved, the gas tail tends to be straight, and the dust trail moves along with the comet in its orbit. So there you go. Those are the general pieces and parts of a comet. The nucleus is the source of all of it. This material starts coming off when the comet gets close to the sun. But that also means if a comet is far from the sun, none of this stuff. This stuff stays in the comet. It needs to get close enough to heat up for this stuff to come off and then to start forming the tail. All right. The exciting part. You may get to see one of these things in the sky. So this is the Purple Mountain Observatory in China. On January 9th, 2023, they reported discovery of what they thought was an asteroid. There were no follow-up observations, so this object was considered lost. So a lot of times these telescope observations are automatic on the sky, and you can either have a computer go through the data, or a computer or a person might go through the data. Anyway, there weren't any follow-up observations on that same part of the sky afterwards. And so if you don't get follow-up observations, you don't see where the thing went. So this object was considered lost, but they thought, we might have discovered an asteroid. Maybe someone will find it later. So there was another set of observations done in February 2023 by this telescope system, the Asteroid Terrestrial Impact Last Alert System. You gotta admit, that is one heck of a name. The Asteroid Terrestrial Impact Last Alert System. So this was developed by the University of Hawaii, funded by NASA. There's 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. It automatically scans the whole sky several times every night, looking for stuff that's moving. And they want to try to find stuff that might hit Earth. So it's a pretty cool system all by itself. But they're looking for asteroids, but sometimes they discover comets. And so they found this object in the sky, and when they did the orbital calculation, they went, oh, it's the same thing that the Purple Mountain Observatory found in January. So that's why the comet is named for both observatories. And the name in the Purple Mountain name in Chinese, in I believe Mandarin, is Zijingshan. And I know I massacred that, but I tried. Zijingshan. And Zijingshan Atlas is the name of the comet. Comet C 2023 A3 Zijingshan Atlas. C means a comet that has an orbit that's at least 200 years long or more. 2023, the year it was discovered. A, the first half of January when it was discovered. 3, the third comet discovered in the first half of January, in this case, 2023. All right. So it's named for both of those observatories, and it is going to become relatively bright in our skies in just a couple weeks. Actually, in about a week and a half. So this comet came from the Oort cloud. And initial data seems to suggest that the length of time it would take for comet Jingshan to orbit the sun once is 80,000 years long. It's a long time. So what is going to happen is I'm going to give you some dates, or either a date or a set of dates, and a direction to look to try to find this comet. October 9th, a week from Wednesday, about 5 minutes after sunset. So you got to wait for the sun to go down completely. You need a clear view down to the western horizon. So we're down to the western horizon, literally 5 minutes after sunset, about 3 degrees above the horizon. That's where the comet is going to be. We're only going to have maybe 10, 15 minutes to view the comet before it sets. Why am I bringing this up? Because the angle between the comet and the sun's light might greatly bump up the brightness of the comet to be about as bright as Jupiter in the sky. That's pretty bright. But notice I said about 5 to 10 minutes after sunset. You got to wait for this thing to go down. And you're only going to have just a few minutes before this thing fully sets below the horizon. All right. So the amount of time to see it is going to be very, very, very short, but you can try. You can try. So week from Wednesday, sunset is at about 6:15, 6:20. Go out, clear view down to the horizon. I don't mean like maybe there's a tree or a house in the way. I mean down to the horizon. Look west. You might see a fuzzy blob in the sky. If you don't see it, don't worry. It's okay. That won't be your only time. All right. So it's going to reach its closest point to Earth on October 12th. So that's when it will be bright in the sky as well. So between October 9th and October 12th, it's going to get a little higher in the sky. It'll get a little bit dimmer, but it'll be still possibly about as bright as Polaris, the North Star, in the sky. So right around the 9th, 10th, 11th, 12th, it's going to get slightly higher in the sky after sunset. Face west, go out, look for a fuzzy thing in the sky. After the 12th, between the 12th, 13th, 14th, 15th, each night after sunset, it's going to get a little bit higher in the sky. It's going to get a little dimmer each night. So your best time to go look for this, that doesn't require you to go look for like 5 minutes after sunset, is between about the 12th and the 15th or so, looking west, southwest, maybe 10, 15, 20 degrees above the horizon. Each night it's going to get a little higher, but a little dimmer, but you should see it, all right? It will help to get a pair of binoculars, try to find it. Not required, but that'll help you. It might help you find it, especially in a light polluted sky. Once you find it, you can then try to find it with the naked eye. You should be able to hopefully see it with the naked eye, fingers crossed. So questions about all these crazy objects we call comets, asteroids. We've got um, uh, leftovers from the formation of the solar system. And it's just really cool that we can study these things and learn about the history of our solar system when we were not around to view this stuff directly. We can study these things and learn about that distant past. All right, questions. I'm going to take a drink of water real quick. You
I always
always
have
have
a
good
question.
you always have good questions.
Okay, well, this is a silly question. This is a, let's say I have a nephew who's really into space and wants his own little piece of space.
Hmm.
And I go online and I'm going to buy a piece of a meteor. Number one, is that
Right.
possible? Number
Yes.
two, how do you know if it's real?
Right. So it depends on who you get it from. So you absolutely can purchase pieces of asteroids online. And there are reputable meteorite dealers. And the one, so I am not a shill for this company. The one that I asked a former colleague of mine, like, there's this array of ones that are out there, which one's legit? And he said the one that he would trust to purchase from is called Aerolite, Aerolite, aerolite.com. And I'm pretty sure this show isn't on anymore, but there used to be a show on TV called Meteorite Hunters. The guy who, I think he hosted the show, he's the Aerolite Meteorite company owner. So he hunts meteorites, he collects them, he sells them, he has people supply them to him. And the only way that they know that these are legit meteorites is you have to get them tested. And it can't just say, oh, that random rock, oh, I saw it fall from the sky, must be a meteorite. Well, no, it has to be tested. And these all the meteorites that that company sells are legit, and they range in price from, you can get um you can get some that are iron meteorites. I'm looking to see, do I have any of mine sitting here? Yes, I do. So you can get iron meteorites. All right, how do I know it's an iron meteorite? Because a magnet will stick to it. You can get these for basically about $1 an ounce. These are mostly iron, um, but they're cheap because they're iron. So iron is just not all that expensive. You can get pieces of asteroids. You can absolutely get pieces of Vesta. You can get pieces of other asteroids that haven't necessarily been identified as to which asteroid they came from. But more than likely, these objects came from asteroids in our asteroid belt. There are also asteroids that come, or there's meteorites that come from Mars and from the moon. And those have been identified because we've got the moon rocks that the astronauts brought back to compare them to. We have all the study that's been done of the surface of Mars with all of our spacecraft and rovers and all that. So we know what Mars rocks are like. And there's other ways to test them as well. But I would say there are other legit companies. It's just that the one that I personally purchase meteorites from for the Adler for our teaching collection that I use, those come from aerolite meteorites. But you absolutely can purchase um, pieces of asteroids, and those iron meteorites absolutely are pieces of former asteroids. And like I said, not terribly expensive. You can get, like, this little one right here would cost maybe um 20, 25 bucks, but you can pay thousands for large pieces, or different kinds of meteorites or rare meteorites and that sort of thing. So
Well, what if you were going out into the world looking for your own meteorites? Is there a place on the planet where it's like more prevalent than not that you might find some?
Absolutely. You can go to two main meteorite hunting locations. Well, three. The first one would be you actually see rocks fall from the sky, or someone sees something fall from the sky, and they know what area to search, right? Because this stuff has been tracked. You've got video, you've got pictures, you've got eyewitness accounts, all that. So that's one way to do it, but that's going to be pretty rare. That doesn't happen all that often. The two main places that they go hunting for meteorites, the Sahara Desert, though especially the Western Sahara Desert, and Antarctica. The reason for those two, if you see rock out in the middle of this giant, vast expanse of sand, chances are it came from space. If you see rock out in the middle of 2 mile thick ice, chances are it came from space. And so those two locations are great places to hunt for meteorites. It doesn't mean that those are the only places where meteorites fall. It means those are the places where it will be easiest to find them. I guarantee there are meteorites all over the place, all around us, and usually probably little tiny things on up to bigger stuff. The problem is a lot of it looks like rock, just like any other rock. So it'd be really hard to find it. But there is another science experiment that you can do. Put a very fine wire mesh netting over one of your downspouts on your house and collect a bunch of stuff. So next time it rains, if it ever rains, next time it rains, collect a bunch of stuff over time. You may take a few rains worth, but the stuff that washes off your your roof, if you run a magnet through those little bits, and there are little bits of metal attached to that magnet, chances are those are micrometeorites. There you
That's
go.
very exciting.
So you might be able to claim that as a meteorite. Now, being this area, the where it is very highly populated, yes, we have airplanes, and yeah, sometimes stuff falls from the sky. Can we truly claim without testing that something is a meteorite? Probably not. But I would say it's a good chance if it's sort of a roundish looking little bit, might be a pretty good chance that it's a meteorite.
Well, so like you say, you could use a magnet to determine, would a metal detector work as well if you were like sweeping the ground or no?
Um, you're going to get every random piece of metal that
Yeah.
has ever been deposited in that ground. So eh, technically yes, but that'll only help you find metal bits, and presumably those would be from iron meteorites. There are stone meteorites and there are rocky iron meteorites. The stone meteorites aren't going to be magnetic. So they're like I said, they're just going to look like
Ah.
any other rock. But we've got three main types of meteorites: stone, iron, and stony iron. The stone ones not magnetic at all. Iron ones very magnetic, and the stony iron ones weakly magnetic. But the thing is, if you think you found a meteorite, don't attach a magnet to it if you want to use it for scientific study. If you don't care, fine, magnetize it all you want. But you actually get rid of some of its inherently interesting scientific properties if you run a magnet all over it. So just depends on what you want to do with it.
Well, I'll
And
be on the
these and
lookout
these are
now.
and these are not silly questions at all. I love these questions because it you can basically point to the source of a lot of these meteorites, and they're from the asteroid belt, a lot of them. And meteor showers, that's your connection to a comet. So when the Perseids happen or the Geminids or whatever, or a random meteor that happens in the sky, a not meteor shower meteor, those were pieces of asteroid belt meteors that are asteroids at one point. So we have this connection to these distant objects. They do come visit us every now and then.
Yeah. I love the analogy to like pollination and sort of like that whole sci-fi TV show kind of, there's life on, these rocks and they're being deposited on the earth and things start to happen. I love that.
Yep. And there's a hypothesis called the the Gaia hypothesis. I think it's a Gaia hypothesis. Yeah, that did life spring up someplace else and get someplace else got smacked by a large asteroid and blew pieces off that traveled through space and land on the Earth. Um, Less likely that that happened, but this stuff that does rain down from these asteroids, these were the building blocks of materials here on Earth. And so would we be here if it wasn't for that stuff falling to Earth? I don't know. I mean, we definitely got a lot of our water because of asteroids and comets. Water, amino acids, all that stuff. It all helps point back to this early connection to stuff in our solar system.
Yeah, and the fact that there is life out there in outer space too. It's not just here on planet Earth, and we learn more about like things that are going on Mars and whatnot. So yeah, that's fun to know. So
Yeah.
yay. Well, if nobody else has any questions, then I guess we're gonna say thank you so much again for another wonderful presentation. It was lovely having you back with us.
Thank you. Thank you so much. And I hope everybody gets to see the comet. Definitely between October 9th and the end of October, after sunset, go outside, face west. It's going to start off real low and then get higher as the month goes on, as it gets dimmer. But you'll see more in the news about it especially over the next week is when you'll start to really see the stories ramp up about this one. So there will be probably handy maps and things, but just remember, go outside, face west. I don't know if I said east, west. Go outside,
West.
face west after sunset. Look for a fuzzy thing in the sky, and you have found Comet C 2023 A3 Jingshan Atlas, and possibly stay tuned for another one that might be visible at the beginning of November. Fingers crossed.
All right. Well, I'm excited. Thank you everyone for joining us tonight, and we look forward to having you back in the future, Michelle.
Thank you so much. Thanks,
All right.
everybody.